Welcome back to the Explainer. Today we're diving into a really massive shift in how we manage AI coding assistants. We're talking about moving away from scattered configuration files and towards source-controlled AI guardrails in Java. Picture this. It's 3 a.m., your pager is screaming, and you are jolted out of a dead sleep. Why? Because an AI agent enthusiastically but totally misguidedly refactored a critical payment component it was never ever supposed to touch. If you've lived that nightmare, or if you just want to make absolutely sure you never do, you're in exactly the right place.
So here's the million or maybe billion-dollar question for modern dev teams. How do you actually stop an AI agent from breaking your legacy code? You've got these incredibly fast, highly capable AI assistants buzzing around your repository. And look, they want to be helpful. But when they stumble onto a highly fragile 10-year-old legacy system that's basically holding the entire backend together with duct tape, they don't natively know they shouldn't touch it.
Right now, we're kind of relying on these out-of-band text rules. You literally find yourself writing out plain English please, typing, "Please, do not modify the legacy payment processor Java. It is highly fragile." And then you just drop that text into some random markdown file in the root of your project. It's exactly like leaving a desperate sticky note on a physical server rack, just crossing your fingers and hoping the AI reads it, understands the context, and actually remembers it when the time comes.
We're looking at a pretty stark architectural contrast here. The old way relies entirely on disconnected, fragile ecosystems. The second you move or rename a file, that plain text rule goes completely blind. Plus, you've got platform fragmentation across all your different AI tools. But the new way, which is what we're really deep diving into today, uses source-retained metadata annotations and unified configurations. This finally brings the rules home to where they belong, planting them right next to the logic itself.
All right, here's our roadmap for today. We'll start with the AI rule drift problem, then look at VibeTags and code-defined guardrails. Third, we'll cover essential guardrail annotations, then move into building the rules engine, and finally wrap up with CI integration and safety.
Let's kick things off with Section 1, the AI rule drift problem, or what happens when context gets left behind.
Okay, so the sheer nightmare of platform fragmentation is very real. If your team uses Cursor, you need a .cursor rules file. Claude Code, that requires a claude.md file. Windsurf needs .windsurf rules. Aider relies on conventions.md. Just think about the absolute absurdity of having 4 or 5 different markdown files cluttering up your root directory solely to tell different AI agents the exact same instructions. Keeping those rules identical and up to date across all those formats manually, it's an incredibly tedious, error-prone chore that literally nobody wants to do.
These out-of-band text files are essentially a giant architectural anti-pattern. We're dealing with 3 core issues here. First up is rule staleness, which is basically the silent killer of builds. A developer simply renames a package, and instantly your AI is flying blind because nobody remembered to update the text file. Second is platform fragmentation, dealing with all that multi-file chaos we just talked about. And third is the total lack of CI enforcement. There is simply no standard mechanism to verify that your AI rules are actually being respected by the build system.
Moving right along to Section 2. VibeTags and code-defined guardrails. Let's make AI instructions a first-class citizen. So what is VibeTags? Simply put, it's an open-source Java annotation processor that utilizes Java's Pluggable Annotation Processing API, or JSR 269. This API essentially gives you compile-time superpowers to act on your code before it ever even runs. So instead of writing those fragile markdown files, you just declare your AI guardrails directly in your Java source code using standard annotations. It becomes the ultimate unbreakable bridge between your raw Java logic and the large language models that are trying to help you out.
Let's dive into Section 3, Essential AI Guardrail Annotations, checking out the taxonomy of control.
You have to check out this number, 39. The one-to-many scaling power of this solution is absolutely massive. VibeTags features an impressive taxonomy of 39 distinct annotations. But here is the real magic. Those 39 annotations map out to configure guardrails for 37 different AI platforms simultaneously. You write exactly 1 line of code, and you instantly educate 37 different AIs. That is maximum leverage for minimum effort right there.
Let's put this into perspective with some real-world examples.
For protection, we have @AI locked, which completely walls off your critical legacy code. For workflow, @AI test-driven enforces a strict red-green refactor pipeline, literally forcing the AI to write tests alongside any logic changes. And for security, consider @AI privacy. Imagine the sheer panic of accidentally leaking 1,000 customer emails into a log file just because an AI suggested a lazy debug print. @AI privacy keeps personally identifiable information entirely out of those AI-generated logs, test fixtures, and autocomplete suggestions.
Now, I know what some of you are thinking. Any experienced developer is going to be highly skeptical about adding arbitrary bloat to their applications. But here's the ultimate free lunch. VibeTags uses retention policy.source. That means the Java compiler consumes these annotations at compile time to generate the AI rule files, and then, poof, it strips them completely from your final .class bytecode. You get all the safety, you pay absolutely zero performance penalty, you add no reflection overhead, and you ship zero runtime dependencies. Literally nothing.
A centralized config file structurally fails the very second a class is refactored, renamed, or moved to a new package. But with first-class metadata annotations sitting directly on the Java class, when the code moves, the rules move with it. Think about the magic of modern refactoring here. When you hit Shift plus F6 in IntelliJ to rename a complex class, your AI guardrails update automatically right alongside it. The next compile instantly regenerates your AI configs, perfectly in sync.
Which brings us to Section 4, Building the Rules Engine. Let's take a quick look under the hood of JSR 269.
So, when the Java compiler fires up, it discovers the processor via SPI and executes it in multiple rounds. During these rounds, VibeTags accumulates the annotated elements. Now, a highly critical design choice here is the use of a linked hash set. Think about the massive pain of non-deterministic builds. If you used a standard hash set, your config files would randomly shuffle their rule order on every single compile. That would result in massive, totally useless Git diffs, which, let's be honest, would absolutely infuriate your code reviewers. Linked hash set preserves the exact insertion order every single time.
Now, multi-module builds in Maven or Gradle pose a unique architectural challenge because the compiler aggressively isolates each module. If VibeTags just dumped rules to the project root, the last module compiled would just overwrite all the others. The solution here is a clever architectural workaround called module sidecars. They basically act as temporary messengers. Step 1 calculates local output. Step 2 writes rules to a temporary module sidecar. Step 3 brings all these isolated rules together in a deterministic merge. And Step 4 prunes the stale sidecars.
And of course, recompiling needs to be blazingly fast. If you blindly rewrite these rule files on every single compile, your IDE will start indexing endlessly and your laptop's fans are going to sound like a jet engine taking off. VibeTags solves this with a 3-layered zero-allocation caching system. First, it quickly checks write cache metadata. We're talking microseconds. Second, it does a streaming byte-by-byte comparison to exit early on mismatches. Finally, it uses a read and compare method that safely preserves any custom user text you have living outside the VibeTags markers.
Look, we all despise tool clutter. VibeTags totally respects that by adopting a file existence opt-in model. Think of it as a polite roommate in your codebase. It never litters, and it only speaks when spoken to. It strictly generates platform rules for files that already exist in the repository. So if you want Claude support, you just create an empty claude.md file. The processor sees it and then populates it. This keeps your project directory impeccably clean of any unused agent configurations.
All right, final stretch. Section 5. CI integration and safety. Failing the build on rules drift.
So, this brings up a pretty critical security question. What happens if a developer, just ignores the annotations, bypasses the compiler completely, and mischievously edits the markdown files directly? Does the whole automated system just fall apart at the seams?
Not at all. Enter check mode, which basically acts as the ultimate bouncer at the club for your codebase. By passing the argument -a VibeTags.check equals true to the compiler in your CI pipeline, VibeTags actively validates the configuration files on disk against the generated rules in memory. It doesn't just throw a warning. If they don't match exactly, the CI build mathematically fails. It physically guarantees that configuration drift cannot enter production.
And as a secondary layer of defense, we have the VibeTags GitHub action. While check mode catches drifting rules, this action catches drifting code. It actively scans pull request diffs, and if a human developer or an AI agent tries to sneak a change into any code physically marked with the @AI locked annotation, it fails the build.
It's a hard stop for regressions, absolutely no exceptions.
Which leaves us with one final, kind of provocative question to think about. If your AI rules don't live inside the source code, right alongside the logic they are supposed to protect, are they really rules at all? Or are they just temporary suggestions waiting to be broken? Integrating AI into our workflows shouldn't mean we just abandon engineering rigor. By moving guardrails to compile time annotations, we can finally make AI safety resilient. So think about how you configure your AI tools today and ask yourself if it's maybe time to upgrade your architecture. Thanks for joining me on this explainer.